Hello, hello. Wow, important announcement. It looks like I have subscribers now. Did not see that coming because I have 9 subscribers and I only have 2/3 cousins watching these videos. So there's people not related to me watching these, which is interesting. So I'm not scaring you off. I'm just saying welcome. I'm surprised you're getting value out of these videos. Sometimes I ramble. But I'm glad, I guess they're helping since you keep watching videos. So I'm going to try to keep making videos to help everyone out, but mainly my cousins still. So we'll go with that. But thank you for those who watch and subscribe. Um, Drop a comment, I guess. Tell me what you use my videos for. I guess you probably have the Abeka book in your classrooms or something like that. Anyway, let's go on with scientific notation. 6.12. Here we go. Let me start by saying that chapter 6 is weird because scientific notation seems to be randomly thrown in this lesson. Because remember, we were talking about polynomials a second ago. So we have scientific notation now, and then the 2 chapters after this are kind of thrown in the mix too. So chapter 6 is weird. But scientific notation is just a specific format of writing numbers because it's more convenient for scientists because it lets them deal with only the important numbers, and it's easier for multiplying and dividing and working with big numbers and small numbers. So all scientific notation is give me 1 second. So all scientific notation is taking big numbers and small numbers and just putting them in the standard format. And the standard format is we write the number with 1 decimal point, or if there's technically that's wrong, but we'll go with it for a second. You write the number so that there's only 1 decimal point. There's only 1 digit before the decimal point. I mean, in this case, it's 9, multiplied by a power of 10. And how do we know what power of 10 we multiplied by? It's based on how many places we've moved the decimal. So for example, in 9,000, we have a decimal point right here. And to get it to equal 9, we move the decimal point 1, 2, 3. So we multiply 9 by 10 to the power of 3, and that's the same as 9,000. And we'll do it again for 70,000. So what we want to do is we just want to rewrite it as a number with 1 digit before the decimal. So 7.0 multiplied by 10 to the power of. So once again, let's find our decimal point. It's right here. And how many times do we have to move it to get it here? 1, 2, 3, 4. So we will have 7 times 10 to the power of 4 equals 70,000. Okay? Now, let's take a look at what small numbers look like. So same thing, we see our 4, so we want to write it as 4 point something times 10 to the power of. Let's count. There's our decimal. And where do we want it to go? We want it to end up right here. So we have to move it 1, 2, 3, 4 times. But what happens if we multiply 4 times 10 to the power of 4? That moves our decimal 4 times to the right. So now instead of 0.0004, we're actually getting 40,000. So what we need to do is actually multiply by -4, because negative means we're moving the decimal to the left. 1, 2, 3, 4, 0, 0, 0, and that's what we started with over here. So let's do the same thing with 0.03. We want to put it in scientific notation, so we know there's just going to be 1 digit to the left of the decimal point multiplied by 10 to the power of, let's see, our decimal starts there, but we want it to end up here. So how many times do we have to move it? 1, 2, 2 times, but because we're moving it to the left, negative. So you can think about it as, because it's a small number, we'll use a negative because negatives are, well, that's a bad way of thinking about it. I take it back. All right, So this is the basic gist. So it's a little bit, not really more complicated than that, but there's a few other cases that we'll look at. So, but what's nice about this is that it's easy for people who use big and small numbers to just compare, because now you can just look at these two numbers and see the important digits, but also see on the scale of what we're working with here. Like for example, when you're talking about how big space is, it's easy to compare two things. The first number doesn't really matter. Like if we're looking at 9 times 10 to the 100th power and comparing it to 8 times 10 to the 3rd power, like these numbers are way different. And we know that because they're getting multiplied by, this number is way bigger than this number. And it doesn't matter so much their leading numbers, it more matters their scale. So scientific notation is putting numbers, formalizing them so that their scale is obvious while still maintaining their value here. Okay, let's take a look at some other examples. So we want to turn both these numbers into scientific notation. So let's start with the top one. We know that we only want one number left of the decimal point, so it's going to be 4 point. And we want to write everything else that we want to go until we hit a bunch of zeros, because the zeros at the end don't really matter so much. So we'll write everything else. So 4.326, we don't care about the zeros, times 10 to the what? Well, our decimal point started, where did it start? Here. Where is it going to end? Here. And how many times do we have to move it? 1, 2, 3, 4, 5. So we know we're multiplying by 10 to the 5. Okay. And let's look here. We want one digit to the left of the decimal, so we got 5 point. Write everything else that's, we'll write the 2, 3 because there's not any zeros after it we have to worry about anyway. We'll multiply by 10 to the something. Let's figure out what. Our decimal started here. We want it to end here. We had to move it 1, 2, 3, 4 times. But because it was a small number that we made bigger, make it a negative. So now these two numbers are in scientific notation. Now let's look at the flip. Let's say we have numbers that are already in scientific notation and we want to expand them out into standard notation. All right, let's say we have these two numbers here. If we have, actually I'll make that a -7. So let's say we have 2.7 times 10 to the 4. How do we expand that out? Well, the 4 just tells us because we move the decimal to the right 4 times. So 1, 2, 3, 4, fill the loops with zeros. And our decimal would technically be there. So that gives us 27,000. And then down here, the negative tells us we're moving the decimal to the left 7 times. And I didn't really give enough space. Okay, so we're moving it to the left 7 times. 1, 2, 3, 4, 5, 6, 7. So we fill all that with zeros. 1, 2, 3, 4, 5, 6. And we add a tack on a decimal right there. So that means this expanded out is 0.000000013. So that's easy enough. So when it's already in scientific notation, it's just a matter of moving the decimals. Negative to the left, positive to the right. And during the break, I realized why they put it in the polynomial chapter of the book. Still a little weird placement, but I get it now. Okay, I have candy in my mouth. So let's say we have 3 times 10 to the power of 6, and we want to multiply that by 4 times 10 to the power of 3. Now, if we didn't know any other way, what we would do is we'd first do 10 times 10 to the 6, which would give us 3 million probably. And then we would do 4 times 10 to the 3, which would give us 4,000. And that would give us a big number that we would have to multiply out a long way. Now, let's use a trick we already know. Let's say that instead of 3 times 10 to the power of 6, we have 3 times x to the power of 6. And instead of 4 times 10 to the power of 3, we have 4 times x to the power of 3. Now this is something we've worked with before, and we actually know how to multiply these together. With the coefficients, we multiply it together, and that gives us 12. And with the variable, we add their exponents. So 6 plus 3 gives us 9. So this is the same as 12x to the power of 9. Okay, so let's go back to this problem here. So let's expand it out using our, because everything's being multiplied together, we can actually rearrange this using the commutative property or the associative, whichever one it is. So we have 3 times 4 times 10 to the power of 6 times 10 to the power of 3. 3 times 4 is 12, and 10 to the power of 6 times 10 to the power of 3, because they have the same base, all we have to do is add the exponents. So that's the same as times 10 to the power of 9. Okay? And so from here, all we got to do is move the decimal's right here, 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is going to give us 12 billion. And so the way it ties into the polynomials, even though I don't think it's the best place, is the fact that because they have the same base here, it's kind of like both of them being a variable that we can combine together into one term. So it was a lot easier to combine these numbers real quick into 12 to the power of 9 as opposed to breaking them up into their big old numbers and then trying to multiply those two big numbers together. Let's take another example. Let's say we have this right here. So if we were to do it the long way, once again, we would have to move the decimal 9 times here and 6 times here, and then try to divide all that together. But let's use a similar example comparing it to variables. So we have 2.25 divided by 1.5 x6, and like we learned in a previous lesson, when we divide, we subtract exponents here. So that 9 becomes a 3, that goes away because 9 minus 6 is 3. So now we're just left with 2.25 x to the cubed divided by 1.5, and then 1.5 goes into 2.25 1.5 times, and so that becomes 1.5. So that becomes 1.5 x to 3. So going back here, we can just cancel out our 10s because they're the same base, they cancel. So 9 minus 6 gives us 3 at the top. This goes away, and so now we're left with 2.25 times 10 to the power of 3, didn't mean to cross it out, divided by 1.5, and that would give us 1.5 times 10 to the power of 3. So it's one step in this case, as opposed to having to make them all big and then trying to divide those two big numbers. And that's really all I had for this lesson. I didn't mean to make it longer than it had to be, but it went on a little long. But that's pretty much it. Scientists will use this. I don't really use it in practice. What I prefer to do, so I'll go ahead and show you the alternate route. Let's say we did have those big old numbers. Let's say we multiplied them out first. 2.25, move the decimal 9 times, would actually give us 1, 2, 3, 1. That would give us that number, and then down here we would have. So if we use our cancellation rules, we can cross out an equal amount of zeros, and then we're left with 225,000 divided by 15. Both these are divisible by 15, so that would give us 1. This would give us 1,500, and that's the same as 1.5 times 10 to the 31, 2, 3, 1,500 right there. So scientific notation, it's just a different way of writing things. It doesn't change the math at all. I mean, you can always fall back on your original principles. It's just useful for the people who use scientific notation. But don't worry too much about it. Just know that it exists and know that's how it works.